let's graph these rational functions by hand. We're going to spend most of our time with number 4 and number 6. We'll go quickly over number 5 and just use that to point out a few differences here. Remember, on page 15 of our notes, we have this long list of steps that we're using to graph these. And up to this point, we haven't really focused so much on this pre-step, but it does show up here today. So just to remind you, we're going to check, first of all, that there is one fraction, because if there's more than one, we have to combine those over a common denominator. And we want to make sure that our fraction is set up in this right format, where your leading term has the x to the some exponent, right? And your constant term in the back. You could have more terms than that, but you want to set it up in this way. You also want to check to see if there's any common factors, because if so, you will want to reduce them. And if those factors exist, then where those factors cancel out, we'll create a hole in the graph. And we're going to look at that example here in a moment. Also today, we're going to take a look at our slant asymptote. We've only been looking at horizontals so far, so let's talk about the slanted case. If the degree of your numerator is greater than the degree of your denominator, instead of horizontal, it's going to be slanted. And if it's slanted, that means it's a line that has slope. And so you need to recall that we use y equals mx plus b to describe the equation of a line. That means we need a slope, we need a y-intercept, and to find that equation of a line, we will use long division. So we'll see that in a bit. The rest of the steps are the same as what we've done before. So here's number 4. We have a trinomial over a trinomial, and that can factor, right? So let's see if we can set this up here. We're going to factor that trinomial into, well, factors of -2, right? So we'll use a -2 and a +1 because we want, no, we want that the other way around. We want a +2 because I want my middle term to be positive. +2 and a -1. And then on the bottom, factors of -6. We want a negative on the middle term, so we want a -3 and a +2. So we do see that the x plus 2's cancel out. That is going to create the hole in our graph. So we'll come back to that in a minute. So we're using this rational function. We have an x minus 1 on the top and an x minus 3 on the bottom. So you might look at this denominator and say, this x minus 3 is the only thing that is creating a vertical asymptote, that is creating a domain restriction. But the original problem had this factor of x plus 2. So that is also creating what we call a domain restriction, a point of discontinuity in our graph. It's not a vertical asymptote, it'll be a hole instead. So when we're looking for the domain, typically we take that denominator, we say u cannot be equal to 0, and that means x cannot be 3. We cannot have an input of 3, so that will be the location of my vertical asymptote. And that's the equation. And then when we take the other factor of x plus 2, and we say u cannot equal 0, then that means x cannot be a -2. That is not a vertical asymptote. That's going to be the hole in our graph. So that's where the hole will be located, at -2. Now we don't know what the y-coordinate is going to be just yet. So -2 comma question mark, we don't know what that y-coordinate is because you can't plug in a -2. You can't get an output to figure out where that is. So when we draw our branch, we'll come back and take a look at where the hole exists in that branch. So that means our domain is all real numbers, but not these two. So all real numbers, but x cannot equal -2 or 3. All right, so let's identify our horizontal asymptote. Right, we're comparing the degree of the numerator with the degree of the denominator. Those are both 1s, so that means they are equal to each other, and that tells us we want the equation of this horizontal line using a over c, meaning the leading coefficient over the leading coefficient. Those are both 1s. So y equals 1. To find the x intercept, set 0 as your output. Again, we're using the reduced rational function, not the original. Set that as 0 over 1 so that we have a proportion and cross multiply. So you have 0 equals x minus 1, x equals 1. Again, write this as an ordered pair. Don't write it just as x equals 1, because then we'll confuse it with the equation of a vertical line when we write that as x equals some number. I don't want to think of this as a vertical line. I want to think of it as an ordered pair, so 1, 0. For the y-intercept, evaluate the function with 0 as an input. So 0 minus 1 over 0 minus 3, that output is positive 1/3. So we have an ordered pair at 0, 1/3. All right, let's assemble what we know so far. We can use a scale of 1 on this graph. We can place our axes about in the middle there. We don't have to adjust them to make the graph fit. So scale of 1, vertical asymptote is at 3. Horizontal is at 1. And we have a X Intercept at 1, 0, Y Intercept at 0, 1/3. All right, so those are the only 2 points that we have so far. Use that vertical asymptote as a separator between your 2 branches. So on the left-hand side, it would suggest we have a branch that is curved like this, but I want a little extra information, so I'm going to pick an additional point over here. I'm going to use, I really want to know, I want to make sure I know what's happening on the left-hand side as well as kind of on the right-hand side of these 2 given points. So I'm going to pick additional points at -3. Notice I cannot pick -2 because that's going to be the hole in my graph. I won't be able to get an output there. So we're trying to pick points on either side of the hole so we can see where the branch is approaching as we get close to -2. And then over here on the right-hand side, you know what, I want an additional point here to fill out this left branch. So how about +2? And then on the right-hand side, I need some points here. So how about 4 and 5 and 6? So remember that with your additional points, you can type these into your calculator. So let's just take one of them as an example. Let's say we've taken that -3 and plug it in as an input. So -3 minus 1 over -3 minus 3. We could simplify that by hand, that's fine. But if you use a calculator on any of these, make sure you use parentheses to separate the top from the bottom so your division bar is in the middle there. Otherwise, it won't give you the right value. So in this case, that'll give us an output of, here I'm using a decimal value, 0.7. All right, so filling in the rest of these, we have a 0.7 as an output. Here we have a -1, 0.5. Here we have a 2, -1. Here we have a 4, 3. Here's 5, 2, and 6, 1.7. Let's add in those points to our graph. So here's the left-hand graph. So you can see how it's curving. That's not really the problem. The problem is what's happening here at -2. I don't have a y-coordinate to plot because there is no point right there. So what we do instead is we kind of anticipate what the shape of the graph will be, and we draw an open circle, that's why it's called a hole, right there. And so that means this branch is going to approach that horizontal asymptote on the left-hand side, kind of skip over that hole, and then as it curves downward, the right-hand side of the branch is going to turn almost vertical as it approaches the vertical asymptote. So right there, that open circle is indicating where the hole is. So notice it's not a vertical asymptote, because if it was a vertical, then our branches would have to curve and run parallel along with that vertical asymptote. But it's just a hole, so we kind of skip right over and continue on the other side. The right-hand side then, plotting those points, suggests a curve like that. All right, I'm going to quickly go through number 5, so I'll fill it in real quick, and then you can kind of take a look at what the results are. All right, let's talk about a couple of features here. So check out the domain. The domain is all real numbers. That means there's no restrictions, so there's no holes and there's no vertical asymptotes. When we try to take that denominator of x squared plus 1, and we say u cannot equal 0, and you solve for x, you get An imaginary value? Well, that means there's nothing to restrict. You can't restrict imaginaries when we're just counting real numbers to plot on a graph. So if there's no restrictions, that means we're having one continuous graph. We don't have two separate branches. You can kind of see the picture down there. Yep, it's one continuous graph. We have a horizontal asymptote at 0. How do we know that? Because the numerator's exponent is smaller than the denominator's exponent. That means it has to be at 0. We found our X Intercept and Y Intercept. There's the work for that, and there's my additional points. So notice, yes, we can touch or cross over a horizontal asymptote in the middle of the graph. That's fine. The horizontal asymptote is really just creating the end behavior. So the right side and the left side of the graph will approach 0 as we go leftwards and rightwards. It doesn't really impact the center so much. And now we'll go on to number 6. You can see here it's describing that we're going to encounter some slant asymptotes. We have not seen that yet, so let's take a look at this as well. Again, that pre-step, do we have a single fraction? Yes, we do. Do we have anything that can factor and reduce? Well, I can factor it, but nothing reduces, so that's just a little pre-check that we have to go through. Here's our domain. Take that denominator, u cannot equal 0, so that means x cannot be a -1. So that's where the vertical asymptote is located at. So I'm using interval notation here. -infinity to -1 in union with -1 to +infinity. I like to do this interval notation from time to time as a way just to remind you that these are the two branches that we're going to be working with, the branch to the left of -1 and a branch to the right of -1, and that will help us know what additional points we might need to pick. Nothing canceled out, and therefore there are no holes. Let's take a look at the horizontal asymptote. All right. We take a look at the exponent of the numerator, the exponent of the denominator. So 2 is greater than 1, so that means there is no horizontal. We will have a slant instead. So if it's a slanted line, then that means we want something that has a slope to it, right? So you might remember the equation of a straight line is y equals mx plus b. So we need a slope, we need a y-intercept. So to find that, we're going to use long division. Going back to that original problem, this is what you're going to use to do that division. The x plus 1 is your divisor. And inside that long division bracket is the x squared minus x. And I'm adding a plus 0 as a placeholder here for the constant term. So we ask ourselves, something times x must give you the x squared. What is that something? We did an x. We'll put that here in the column matching x to the power of 1. Distribute that to the divisor. So x times x is x squared. X times 1 is 1x. And then remember, you have to subtract each column. So when you subtract the x squareds, they cancel out. Here, when you subtract, you have a negative x minus x, that's a minus 2x. Bring down the next term, which is just a placeholder of 0. And we repeat the process. We need something times x to get us that negative 2x. So we need a minus 2. Distribute. And then remember, you are subtracting each column. So subtracting a negative is the same thing as adding a positive. The 2x's cancel out. 0 minus a negative 2 is the same as adding a positive, so 0 plus 2 is 2. That's your remainder, right? We have no more terms to bring down, so that's your remainder. What we're looking for is the equation of a straight line. There it is. So in other words, throw out the remainder, you don't need it. You're really just looking at this part here and saying y equals that. That result is the equation of the straight line that you need. So y equals x minus 2. That means you have a slope of positive 1, and the y-intercept is a negative 2. The x-intercepts, I'm going to skip the work just for time, but if we were to set this equal to 0 and cross-multiply and solve for your x's, you would get 0, 0, and 1, 0. The y-intercept is just at the origin as well. So let's go ahead and set up our graph. Again, we can use a scale of 1s. the vertical asymptote at -1. And our slanted asymptote has a y-intercept of -2, and then a slope of +1. So up one to the right one, up one to the right one, and continue that pattern in both directions. So again, with the vertical asymptote at -1, that tells us that we'll have a branch on the left side of that. So somewhere over here on the left-hand side, we need some points to plot. And then on the right-hand side, we need some points to plot as well. Of course, we have some X intercepts. So we have one at the origin and here at 1, 0. So we have the right branch mostly there. I would like to pick an extra point just to make sure of my curve. So maybe some additional points such as these. For the left-hand side, I want inputs of -4, -3, -2. And then maybe on the right-hand side, I want an input of +2. So using my calculator, I have -6.7, -6, -6, and +0.6. So those are the 4 outputs. Let's add those points in. You can see those points are bundled really closely together. So that means that we have a pretty sharp turn. As we approach sort of that inside corner, we're going to have a sharp turn. And the right-hand side of that branch is going to approach the verticals. We approach the vertical asymptote. And the left-hand side of that is approaching the slanted asymptote. So on the right-hand side then, we see pretty much the same pattern. The left part of that branch is going to approach the vertical. We have a pretty sharp turn here in that corner. And then the right side of that branch is slanted, approaching that slant asymptote like that.